So in this session we'll be doing purely simulation. I'm giving some exercises. We try to solve them on Simulink or on the CISO tool. CISO tool, or we call it Control System Designer app. Okay. So let's take this transfer function 1 over s plus 1, s plus 2, s plus 10. Alright, so let me run it. So this is my open loop transfer function 1 over s plus 1, s plus 2, s plus 10. I call it open loop OLTF, open loop transfer function. Then it is when I execute the program, this is my open loop transfer function. Okay, so what's required now, you go to the app, and in the app Control System Designer, design single input single output, or CISO controllers. Okay, so this is the Control System Designer, we call it CISO tool. Okay, so if you click on it, you get a system like this, where you will find the body editor, root locus editor, step response by default. Body editor magnitude and phase, root locus imaginary axis and real axis, and step response function of time. So now, for now, let me just focus on the root locus. I'm not going to study the body controller design using body flow. We are studying now, focusing on controller design using root locus. So let's say Control System Designer, or CISO tool. Okay, I just take this to here, just to arrange them differently, and here maybe I expand it. So if I close this stuff, so I get the step response here and the root locus. So I can look to the step response directly by changing my root locus. Okay, so these are the architect. So see, this is the current architect you are using. So you could choose to use different architect. You see, your controller C becomes here. Okay, this is one of the architect where your controller is in the feedback. Of course, you know, you have a noise, you have disturbance on output, noise on sensor, disturbance on the control signal. Alright, you have filter before the reference. You can, by default, they are actually 1. All are 1 by default, everything is 1. So this is another architect. Different architect you could see. And you know, many of them we saw in our class, like basically this architect we saw something similar. Okay, this architect, so you have G1 and G2. Maybe your plant is divided into G1 and G2, and you have controller here. Okay, or this architect, you have actually 2 loop, controller for the inside loop and another controller for the outside loop. Alright, so you need to define all of them by default oral. So, well, I consider this classical only by default. I keep h equal according to here. So I have feed h sensor equal 1 unity feedback. So the only thing I will change is the open loop transfer function. So I'll put, instead of g, my open loop transfer function. Open loop transfer function, which is defined on my command window, so I can add it this way. Alright, then I click. So you see here, you find the root locus and the step response. If I click on G now, so Z is the open loop. H is 1, C is 1, F is 1. Okay, so then that's again 1. Let me look to the preferences here. This is very important step. You need to do each every time. I recommend you to do each and every time you open your Control System Designer app. make sure the units are appropriately, and go to the option, and I recommend you to use 0 pole gain format. All of them are format for the controller. You can represent it in any format you wish. Basically what you see here, like this is your controller C of S, right? C of S. So this format tell you want to represent it as this, how this format, 0 pole gain, or you could represent it in different formats like DC gain 1 plus S over omega Z over 1 plus S over omega P. And this format, like a filter, you present it by a filter, but at the end 1 over omega Z, 1 over omega Z is, or omega Z is the cut-off frequency. Okay, so you can represent it this way. This we call it natural frequency format. Alright, so you can represent it this way. Or you could represent it also in the time constant format, so DC or DC gain, then 1 plus TZS over 1 plus TPS. Alright, all of those are representation. Well, we recommend this representation, and that's the one we will be using in our course. 0 pole gain, but at the end all you can convert them from one to the other easily. Like if you want to convert from this to this one, basically okay, you take Z comma here, so you get Z, then S 1 over Z S plus 1. If you take P comma here, so 1 over PS plus 1. If you look at them, then K Z over P is the DC gain, and 1 over Z so is omega Z. So this becomes your frequency, right? 1 over Z is 1 over omega Z. So Z equal omega Z and P equal omega P, and DC gain is K Z over P, right? Or also you can convert it to this one. So now DC gain KZ over P, and TS is 1 over Z. TP is 1 over P. So at the end, but I recommend you to use the last one. Alright. So I apply. Then now look, what's this dot that you can see here? Let me zoom a view. You see Rootlocks editor. I can click here and I zoom a little bit, maybe more. Right, so now I click again on this. Look, if I pick this pink color here or here, the same, so, and start moving them, you see when you move one, the other are moving. You see this gain, you move them, they approach each other. Also this was moving, and you look to the step response is also moving. What's happening here? This is also moving, but you cannot see because look, see, it's moving as well. So when you click on any one, you are moving the 3. What's this? What's happening? Look to the value for the controller. Now it's not 1 anymore, it's 24. So this is your gain K. By change, this is not the gain K, this is the gain K. By changing the gain K, you are changing the closed loop poles locations. So you know, at K equal 0, you had, this is at K equal 0, K equal 0, and k equal 0. Then here at a given k equal 24, here is k equal 24.164. You see, k equal 24.164, and here is k equal 24.164. So then that's your controller now. C is 24, and you have the plant, which is open loop transfer function. You have, and here is your system. That's the reference. That's y minus plus. Okay, I have filter equal 1 here and unity feedback. So you are looking at the step response. You are looking at y by applying a step input, unit step input, and you are looking at y. So see here 0.55 somehow at this gain. So we didn't reach the steady state. So if you click on it, right click, for example, steady state error, you see final value is 0.55 approximately. So still didn't reach the, and you have overshoot. You can look at peak response and you can see the overshoot. Alright, so now let's keep increase gain k and see what's going to happen if I do that. Okay, keep increase, it's 37. Okay, so final value is 0.7. You know, here by default the step is always 1. Alright, but if you wanted 4, it's same thing, same controller, you could use it for 4, for step input of 4. Or if you wish, have a prefilter equal 4. As simple as that, right? So now if I have my prefilter equal to 4, I double click on it directly if you wish, and then I go and put it 4. So see now it becomes, so you have here 4. Okay, so that's simply, that's like, because you remember the architect you have. Edit architect, these are your architect you are choosing. So if here, just multiply by 4. So now I return it to 1. Alright, so go to the controller, it's 98. Alright, so for example, so now 0.89 still didn't reach the steady state. I have a lot of overshoot. 0.9. Alright, 0.925 means still not at 1. That's the one. Alright, let me go to the here, and now as you can see, so I will delete here, and in zoom I click on zoom, right click, maybe restore view, return to the original view, and then I click here. Okay, so we are about to become unstable. So I click, okay, 0.9, but you have a lot of overshoot. Oh, if I go over it, so it becomes unstable system. So now you're able to know, you know how to use this ISO tool. That's how to use this ISO tool for proportional controller. So let's see their question done now. I put this as in the ISO tool. They asking you in this exercise, well, that's your system. That's your system. What we are doing is we're adding on it not only the gain k, compensator equal to s plus 0.1 over s. So that's your compensator, s plus 0.1 over s. And then they're asking you show that the additional of the ideal integrator compensator. Well, shown in figure 9.4b reduces the steady state error to 0 for a step input without appreciably affecting transient response. So without affecting this transient response, by adding this compensator now, not only gain k, s plus 0, 1 over s, we are reducing the steady state error to 0. So let's add this compensator, s plus 0, 1 over s. If I look to my M file, I don't have it. So here is my compensator. For now, add pole. So I will add integrator 1 over s. Also I will add 0. Right click, real 0 at where the damping look is the location of. Here is the location at 0.1. So s plus 0.1. So look at it now. It's s plus 0.1 over s. Well, the gain k we can change it later on interactively. But that's my system now. S plus 0.1 over s. That's my controller. Look at the data given. S plus 0.1 over s. So s plus 0.1 over s. So how I did, I right click, add poles and 0 integrator 1 over s, then real pole or real 0 depends. So in this case we need real 0, we need complex 0, we need etc. So now I need real 0 in my, and it is at 0.1. So s plus 0.1, so then the location is at minus 0.1. So that's my control. Again you can play. So you see here you have 0 and pole. So 0 and pole very close to each other. See, 0 and pole here very close. This one as 0, one as 0.1. So they are very close to each other, and this is very important. We'll talk about it later. Why did we choose them very close to each other? All right. So let me tune now and see. Actually, even without tuning at small value of gain k, or even, so it's up to you what value for gain k you want to take. But actually, the system final value is 1. It seems like if I have small value of k, like here very small, or why I don't take it as 1, just k equal 1 as it was, and this my system looks like this, and I can find the settling time. Well, settling time is 800 seconds, so much. So you can, in this case, retune it if you are not satisfied with. So I click on it, so it appears this bottom here, this tab here. So I click, just I want to zoom a little bit. Alright, so are you satisfied with 400? Depends on, still like not. Maybe we want to decide to have some overshoot maybe. Alright, so 50 settling time is 50. So faster now at the beginning. Alright, it's a settling time, and you can also check the final value always 1. Okay, so you can get even less settling time, so make it faster, but with the cost of some overshoot. So depends on the criteria you want. Okay, so now you know how to add the controller to your system. Let's try to analyze it. Given the system and figure operating with a damping ratio of 0.174. So now we learn the tool itself. I'll go with you on analyzing and see what they want actually from us in this specific exercise. What I did for you, it meant like as a presentation to the tool itself and how to use it, but with this given application. So given the system of figure 9.4a operating with a damping ratio of 57.4. That's the damping ratio, 57.4. So then, operating with a damping ratio of 57.4, I will go now to the system. I want to operate it with a damping ratio of 77.4, or yes, with a damping ratio of 57.4, because this is 0.174 damping ratio zeta. I can convert zeta to overshoot. How to convert zeta to overshoot? I can go to the solver or online, or I can doing it using the graph I'm giving to you or the equation. So 0.174 0.174 solve for overshoot 57.4. So see, just a 57.4. So it operates, this system figure A operate at 57.4 overshoot. Now let me then retake my controller back and delete and let's check now what's going on. Overshoot of 4. No, they said operate at 57.4. 19, so more than that. 40, more than that. 52, less. 55. So now if you don't get exactly, so now maybe you can come here, put 180 and check. 180, 57.5, and then it is alright. 57.5. Okay, so then operate with this condition, and this is settling time. So they are telling you, show that the addition of this compensator reduces the steady state error to 0 for a step input. Not maybe for a ramp is differently, for a step input, without appreciably affecting transient response. So settling time at this overshoot is 5.69. that's the settling time, and yeah, and the steady state error, it is 0.9. so see, so I don't want to affect the transient response. Now I add a compensator that doesn't affect the transient response, which working at 57. So this is what they said. So the transient response currently is this one. So now adding this controller, the compensator, will reduce the steady state error to 0. So they will cancel the error. So now I don't have, so you see it's 0.9 final value. So I have an error of 0.1 to reach the 1 step. So then adding this compensator, it reach 1 without affecting the transient response. Okay, first thing I will teach you now, let me store the data. So I store it as design1. So now it's stored, I can return to it to comparison. So now I go to my here, maybe return it back to 1 is alright, and I will add an integrator, and I will add a 0 and the 0 is at 0.1 as they ask us to do. Okay, so we have a gain of 10. Alright, so let me put a gain of 1. Should not affect the transient response. So operate at how much? Operate at 57. Overshoot. So overshoot of 57. So keep increasing the gain. 46, 56. So then maybe 225, maybe 227, 57.3, and here is 57.4. Okay, so that's the one. So look to the settling time, final value, and settling time. Well, and let's do the comparison between both. So I return to the same overshoot, but this is it doesn't clearly saying the final value is 1. So there is no steady state error. But what about settling time and peak time, for example? Let's see them. So now that's my second design. So now if you wish, I can also store it if I want. So I say store, so I have two design. Then I click on the comparison, not in store to save them. I see this is design 2 currently, so I click on design 1. So I'll be showing the two designs at the same time. So basically you see the difference in errors. This is reached steady state better than the design 1, which is without compensator and doesn't affect the transient response, in the sense doesn't affect the overshoot of the system. It affects the settling time but doesn't affect the peak time and the overshoot. So I have same overshoot 57, 57, and same peak time at the same peak time. So that's the transient response characterized by rise time, peak time, and overshoot. Well, settling time is more for when it is reached a steady state. So this is affected, of course. It makes more sense that the system becomes slower when you add integrator. System becomes slower in the sense it settled slower. But in terms of rise time, overshoot, peak time still the same. So that's how we answer the question. We show that. That's how we showing it. Alright, here is some information for you. They are saying the compensating network, this network is chosen with a pole at the origin 1/s to increase the system type, of course, increase the system type, and a 0 at minus 0.1, 0 at minus 0.1. Why? We choose it close to the compensator pole. So 0.1, if you remember here from the root locus, 0 and pole, we choose them close to each other to cancel the effect of each other, so that the angular contribution of this compensator s plus 0.1/s evaluated at the original dominant second order pole is approximated. So this the angular contribution of the compensator is approximately 0. So because the 0 and pole are close to each other. Well, original dominant second order pole, this original system is a dominant second order pole. You can see that you have S1, S2 are dominant pole, S far away from, so can be neglected. This third order system, S plus 10, can be neglected. So it's a dominant, it's a dominant second order pole, basically. Yes? So that's what they did. All right. In this first exercise, I already did it myself some times ago, and I'd like to show you how to open it, how to open a session. So how to save a session first. Save, like I call it student demo. Okay, exercise 1, student demo. So that's how to save a session. So my session is saved. So at any time I can reopen it. Like I go now, I open my exercise 1, put locus exercise 1. And now it takes some time, but it will open. So see, but maybe when it opens, you need to yourself redistribute them in a way. So see, they are, I have the same result as the one I show you in a while, right? This is my compensated system. That's how to open it. Open session and you open it. It's saved as .mat file. Alright, that's for exercise 1. So now we'll go and practice more and more, see different variety of problems, so we'll be able to master the CISO tool much better. So yeah, we open the Control System Designer app and you work on. If you wish, you can directly integrate S+01 over S as part of the plant, and you vary the gain K, or you do as I did just now. So now we see different variety, different things, exercise 2, and all using the CISO tool, so you will master different variety of problem using it.